Okay, for record, 2 students in class. Katana not yet logged in. Right. Okay. Let's go through what we have covered for the last in our last lecture. Let me know if you're not able to see the PowerPoint slides on your screen now. Okay, we are now in chapter 2. So today we're going to cover most of it. Right? So again, for chapter 2, there will be one question from this chapter, either in your test or final exam. So the fundamental equation that you should always remember is F equal to KD, force equal to stiffness matrix, stiffness times the displacement. D is a displacement. And you should differentiate, you should know how to differentiate when you want to analyze a single element or assembly. Okay, when you do assembly, you use the capital. If you look at a small element, you use F. Okay, a small F. K also small when you analyze element. But if you do assembly or combined system, then you use a capital F, K. D still remain as the displacement matrix. Okay, and we already cover a spring structure with two location, two node 1 and node 2. And this two node is free to move. And we already discussed how we convert a spring system that you see on the screen now. This on the left diagram, spring structure. You convert this spring structure, you write in the matrix form, which is F equal to KD also. And the form that you see on the screen now on the left, this one is an expanded formula. So during the exam or test, remember to change accordingly. Yeah? So if you look at a single element, then use a small f for your force, small k for the stiffness, and remember to change your displacement into the direction. Okay, no, don't use the small d. Change it to the direction. So for example, if your structure go into x direction, then you use u, y you use v, z you use w. Okay, so remember on this one. Of course, in your test, most of the time you won't see x direction. Okay, I will change this one to either y or z. So remember to change this one. So they give you some hints on what is going to come out in your test or exam. All right. Then there are 7 steps. Today we're going to repeat these 7 steps in your question or in your tutorial question. Right, there are 7 steps. First, select the element type. So we have 3 elements. All right. So if you're not sure, then you have to go back to the previous slides. Okay. Second one is to find the displacement equation. All right, we have a linear, quadratic, and polynomial equation. All right, first choose type, whether it's a 2-node, 3-node, 3D symmetry type. Then you go for equation. Right, look at the equation. What is the equation that we deal with? Normally we only deal with a linear, and then sometimes if it's a polynomial, then you'll be given a polynomial equation. Okay, so most of the time you'll see spring structure. So spring structure callbacks the Hooke's law, F equal to Kx, right? So F equal to Kx is a linear. So most of the time it will be direct case. Then number 3 is to solve the strain or displacement and stress or strains relationship. Okay, so we already explained all this in a previous lecture. All right, how to get this one down. Number 4 is to look at the stiffness matrix, which is your K element. All right, so you convert from your free body diagram into the equation for individual point, or we call it node NODE, node, individual node. So each node will give you an equation, right? And at the end, you will get this expanded stiffness matrix equation. So you'll get F on the left hand side equal to stiffness matrix K and the displacement in U, because the structure move in X direction. Again, if your structures move in Y, this component, your displacement will change to V, all right? And if I change the axis to Z, then this one will change to W. So be careful on the axis that are going to change during your test or exam. So this one, be careful, right? These are the tricks that I'm going to give to you guys during the test. So be careful. All right. Yeah. So today we're going to look at this equation. So this is 2 by 2. So in later, I think in second session or later on, you will see 3 times 3. So if you do not understand what is 3 times 3, 2 times 3, you need to go and read the appendix A, right? Right, then step number 5 is just to solve the unknown in the equation, right? So you just key in the boundary condition. So the first step to solve this equation, this matrix equation, is to find the boundary condition. Means that you look at the constraint on the point, whether it's moving or not moving, right? So step number 5 is look at the boundary condition, all right? Then number 6 is to find the displacement. So you have F equal to KD, and you look at the global dimension. So you look at this component, displacement component. So you look at individual, you look at the displacement at the point. So yeah, you solve for the, in this case, X direction, you solve for the U. And then you solve for the, step number 7, you solve for the, after you solve for displacement, you solve for the F, right? Okay, we look at the example. So this one is one example. So if you already download or print out your tutorial, this one is in your question number 3. Okay, question number 3, you're given a 2-spring structure, right? 2-spring structure. You have spring number 1, which is give you this symbol 1 and circle. So from one point to this point, this node to this node, and then combine with spring number 2 given by this symbol. So spring number 2 have 2 nodes, node number 3 and node number 2. And this spring, this assembly of springs was moving in X direction. Okay, moving in X direction. And there's a pulling force at point number 3 or node number 3 and node number 2. There's a force in point number 2 and point number 3. K is a stiffness for spring number 1, K1. K2 is a spring stiffness for spring number 2. Okay. Any question for the diagram that you see? Any question you want to ask me? Anything that you're not sure, or anything that you don't understand? All right. Now the question asks us to determine the total structure stiffness matrix for a spring assembly by using the force displacement matrix relationship, which is this one. This one, this equation, F equal to KD. So expanded F equal to KU in this case. All right. So what we can see here is you look at the constraint before you start anything. You look at the constraint. So node 1 is mounted on a wall, with its node 1 is fixed. And then there's a 2 force that we explain. Then we look at the general direction or global direction in X direction. So we look at element number 1, which is spring number 1. We break this, we look at a single element first. One spring by one spring. So for element 1, this means spring number 1, again, in this case, this is a simplified or free body diagram. It can represent a steel bar that able to expand. So you can change a aluminum bar into a spring free body diagram. Okay. So for element 1, okay, let me check. Okay, katana is here. Okay, good. All right, so for element 1, we write the stiffness equation that we saw just now. Okay, we only change the small denotation. So this equation that you saw on the screen just now, this one, F equal to K matrix times the displacement matrix. You just change the small numbering here. Okay, so you just look at the diagram and then you just change the formula accordingly. So if you're looking at element 1, you only have 2 nodes here. So node number 1 or position number 1 and node number 3. So what you do is you go to the formula, you change to F1x, 1 represent point number 1, x direction, and force, because this point is represent point number 3, so you write small f, 3, and x direction. So there's a small column here, 1. 1 represent the top column here. 1 means element 1. Okay, 1 means element 1. So any question about how to write the force? Anything that you're not sure? Why suddenly this one 1x? This one suddenly 3x? Who don't understand? Ask me now. Huh? Okay, seems all of you are all right. 3 of you okay. So we continue with the K matrix. This one, because this is a standard spring structure that they already derived from the previous slide. So it's a standard. So you just copy the K. So K, the first one is positive, second one negative. This one, the third one is negative, this one positive. So if you don't understand why this one negative, this one positive, go back to the previous slides. And remember to number correctly. So if you're referring to element 1, the stiffness matrix inside there, you should use a K1. So if you're referring to 2 later on, you will see this one change to 2 already. Okay, K1 minus K1 minus K1, K1. So this is the stiffness matrix. And then your displacement. Again, remember to change the displacement to the direction that you're referring to. So this one, you're looking at x direction. So change this one to U instead of D. Don't use D here. So U, and then this is 0.1. And then this one 0.3. And you're referring to the first element or element number 1. That's why you use this symbol, right? 1, and then there's a column there. Okay. Now, let me ask you, right? By looking at the screen now, if you look at element 1, if I want you to write the stiffness matrix formula expanded format like element 1 for element 2, what would you write? Okay, what would you write? Okay, I'm going to ask Katana for force, Singi for K, and Lai for the displacement. Okay, so Katana, what is your answer for the force or element? If I want to write for element 2, what would you write for this element 2? What will you write for the force component?
We'll have F3x,
3x, and then
then F
and then what is the number above the 3x?
3.
3. This one, this one 3.
Yes, it's from here.
You're referring
yes.
to element number 3 or element number? This number referring to element number, this one number 1. That's why element 1. Let's put 1 here. So if you're referring to 2, what is the number for this one?
Should be 2.
Yeah, should be 2, correct. Then
Yeah.
then followed by, you only answer one answer, and then for point number
Then
2, what do you write?
then f to x.
2x, and
Then 2.
then 2, correct. Okay, for your average, this one. Okay. Singy and Lai, do you have any question on Katana answer?
No.
Okay, good. Lai, you okay, yeah? All right. Now we continue with Singy answer. What is your K answer for element 2?
K2, negative K2, negative K2, K2.
Correct. All right. Then Lai, what is the answer for displacement for element 2?
U2.
U2. Why U2? 2 is here lah. 2 is here lah. But why this one become 2? Look at element 2. What is your first point? What is your first point number?
3. U3.
So this one is U3. This one, what's the number?
2.
2. Okay, then this one? U2. U2. And then this one? Come. This one is what? What number?
2.
2. Okay. Right. So these are the answer that you give us. So correct. All of you able to answer this one correctly. Okay. So in your coming test, it's going to be a similar question. Of course, I will change the direction. So displacement will not be U. Okay. And of course, be careful on the numbering that I give you. All right. So maybe I'll play around with the note there. So maybe I will pull the wall to the number 2 position. But anyway, the format still same. So I think the first step have no problem, or be able to answer correctly. All right. So you saw for first step is that you write out the matrix format for F equal to KD, expand them, and then you're referring to individual element or individual spring. Okay, right. Now, one concept that we should always remember when we have an assembly of 2 spring structure, we will need to remember the law of continuity. The law of continuity. What means by continuity? It means that if you pull in one point on the right hand side, in this case, you have a force in at a point number 2. If you pull on this side, point number 3 will experience expansion also. It means that the force at number 2 will affect number 3 and have an effect on spring number 1. It means that the force able to affect the other structure. Okay, so it means you pull number 2, number 3 will continue to move also in the same direction of number 2. So this is called continuity. This is a important principle when you learn about FEA or finite element analysis, FEM. Okay, and also this is a continuity concept that you must remember if you use CAD software to do simulation, right? Any software that did FEA analysis, they all based on continuity concept. Okay, yeah. So if you write in mathematics form, you can write in this way. It means that this displacement in point number 3 for element 1 will be same as displacement in point number 3 for element number 2. Which means that because of continuity, displacement on number 3, the connecting point will be the same. It means if you write mathematics, U31 equal to U32 equal to U3, means the displacement at point number 3 will be the same for structure number 1.3 and also structure number 2, point number 3. displacement here will be the same. Okay, so at this moment, you should be able to clear. If you look at this formula, U31, what does it mean? U32, what does it mean? Okay, U means displacement. If you see V means in the Y direction, if you see W means in the Z direction. Okay, now we break the assembly into free body diagram of each element. Okay, I'm going to show you the answer. So how do we break this assembly? You break it by using the point that given. So the first point you look at is point number 1. So this structure. Okay, point number 1. Okay, and the direction of the force here, later I will explain. So the first step when we break our assembly into a individual element and node is that you first step is that you break the node first. So the first node you have, and then if you break the first node, then you followed by the spring structure. So you see the second spring, the spring number 1 here. So first diagram, second diagram, third diagram is a node number 3, which is this one. And then followed by the spring number 2, which is this one. Spring number 2 with 2 nodes. And then individual node of number 2. Okay, so we just break the 2 spring here into 1, 2, 3, 4, 5. Okay, don't worry about the direction of the force first, but try to understand how we get 1, 2, 3, 4, 5. How you get these 5 individual free body diagram. Okay, try to understand. So you break number 1, spring 1, point number 3, spring number 2, and point number 2. Okay, now the direction I'm going to explain now. So in this case, we do not know the direction of point 1. We do not know the direction number 3, but we know one direction for sure, which is the direction of the force number 2. It's pulling to the right in the x direction. So what you do here, you try to look at the 5 diagram here, 1, 2, 3, 4, 5, and then you start with something that you are sure. So in this case, we are very sure that point number 2, force to the right is confirmed. So what you do is that you draw F2x to the right first, okay, to the right, and all the diagram is in equilibrium, means all the force equal to 0. So you need to balance the force. So the first steps, I use a pen. So you start with this one. Okay, you start after you draw the 5 element, then you start with the force that you know. So start with this force, and then you look at node number 2. You try to balance the force. So you try to balance. You have force to the right, then you must have the force to the left. So you have clear element node number 2. So this is step number 2. Okay. Any question? You're not sure how to draw the force for the point number 2? Any one of you not sure? Why suddenly the direction become this one? Okay. Ask me, stop me if you're not sure. If you're lost already, stop me and ask question. Okay. Now then you continue. Because you start from the right, then you continue to the next element. Because this is to the left, then point number 2 for element 2, this one, you draw the direction opposite of this one, right? Because this force at point 2 to the left, so it must balance this force. So to balance this force, you draw an opposite direction. So this is force number 3, right? And you label accordingly. So you know that this force is F2x. Okay, F2x. Then you continue with this element. Continue. So this one is a little bit complex a bit. So we do not know the direction of this one. All right. But you look at the diagram. Yeah, you look at the diagram. Now, if there's no F3, then the direction will be balanced. If no F3x, then the element will become like that. The force on element 2 will become like that. The force on the left hand side will become balanced to another side. So this is if no 3x. However, this case we have 3x. So you continue with the diagram. So what you do, you start with 1, 2, 3, and then you go to the element 2, you look at point number 3, you have a force there. You have a force F3x. F3x go to the right. So what you do is just copy the direction of the force given. So we go to the right. So you just include what you see in the given diagram. So we have a direction to the left. So in this case, to the left. Okay. Let's go to the left because we have force. So in the test, maybe I will change the direction to the right also. So you need to depends on the diagram given. Then you continue with point number 3 or node number 3. You just balance this force. Okay, you just balance this force. So you have a number 4 step here. To balance this number 4 force, you draw opposite direction. Okay, yeah. Then you do not know the direction of this one. You just stop for a while, and then you go for point number 1. Okay, now point number 1. Point number 1 will be it can be in this. If you look at point number 1, the textbook give you the compression force here. So if you're not sure, you can draw like that. Okay, you can draw like that, and then you balance the other force. However, later on, the force you will get if you draw opposite direction, you will get negative answer. Later on, you'll get a negative answer for the diagram that you draw. I already explained why there's a negative sign there. I already explained in the previous lecture. Okay, so the textbook assume that force at point 1 is a compression force. So it go in like that. So point 1 go in like that. Then you look at element 1. Element 1 have both sides. So you just counterbalance the force that you draw in a free body diagram. So this one go to the left. So on this point, you go to the right. Okay, and it come to this point. Now it come to this point. You know that because point number 3, because if you look at element 1, point 3 is go to the left, right? So you go to the left. There's a F3x on for element 1, this point. The 3Fx is confirmed for sure that it go to the right. So the direction for point number 3 is go to the right. Okay. Then you counterbalance for point number 3. Node number 3, you counterbalance. So this one falls to the left, to the right. Then there's a component that opposite counterbalance this point. So there's a force. That's why we draw there's an arrow to the left for point number 3. Okay. Right. So we already solved this one, and we know that point number 3 here also have one more direction, which is F3x here. There's a force, external force. There's an external force here, right? Okay. So be careful. There's this one, this one, this one, this one, this one. Let me erase. this one, this one, this one, and this one is all internal force or internal displacement or internal force. This one, F2x and F3x are external force. So this one you extract from the diagram, from the diagram here. Okay, any question you want to ask me? Any one of you not sure how you convert a system to an individual free body diagram? So if when it comes to tests, the conversion from here to individual, it might give you up to 5 points or five marks. How I give you marks? 1 mark, 2 mark, 3, 4, 5. It's very easy to score for this module. So I will be very generous in giving marks as long as you follow the steps. Okay. Yeah. Any question? Yeah.
Yes. So I've not really understood much on the splitting of the system, because is it like the spring part that you consider an element, or
Okay.
yeah.
Yeah. All right. Now, okay. Now you're not sure how to break the system. What is system? What is element? So this is a system, a complete system, which is mean the assembly system. Okay. Then you break this one. You can break into 2 spring, right? This is 2 spring that you'll see if you break. So spring number 1, spring number 2. Okay, but to do analysis, you need to look not only the spring element, you need to do spring. You need to do spring element plus node analysis. So you break the spring, the system into spring plus node. So how many node you have here? So you have node number 1, node number 3, and node number 2. So you combine the system from spring plus node. So that's why you get 5 diagram here. 1, 2, 3, 4, 5. Catalan, do I answer your question?
Yes, I'm getting there.
Okay, right. All right, now we break the system into free body diagram already, which means we have 5, and then the direction was given. And the next step is to name the force that you draw in the free body diagram. So after you draw free body diagram for individual node or element, then you put in the number or numbering for the force. So for the node 1, you have 1 F1x means the force at 1x. And remember, you see at on the screen now, you have capital F here, means this is the external force. Capital S for external or global force. Global, external or global. And then there's a small f in the diagram. Small f means you look at the element. Yeah, be careful. There are 2 detonation. Capital F and small f here. Okay, be careful on all this numbering, because once you clear on the numbering or notation, then you should be no problem in the analysis. The rest is just the mathematics steps. Okay, so this is just a small reminder when you convert system into element. Be careful on the capital F and small f. So if you look at the big picture, then you use a big F. Like for example, 0.1, capital F1x here, because this is on the constraint point number 1. and then you look at internal from point 1 to point number 2, all you see on the screen here is a small f, small f here. Small f means the internal force or element force, and there's external force at point number 3. That's why we pull the we have an additional arrow here with a capital F x 3x here, and then there's a capital F 2x at the point right hand side of the point number 2. Okay, so then we're going to look at individual point put in the matrix form. Okay. All right, then we equalize. We start to write equation already in equilibrium form, or all the force equal to 0, or we put all the force in the equation. So if we look at point number 1, what you have here is capital F1x will be equal to small f 1x, and with the high number 1 here. So you should understand why what is all this? What is small f1 in? What is why here we write 1x and there's a 1 here? It means it refers to element number 1. Okay. So any question on the first equation we see on the screen now? Any question? Anything that you're not sure why suddenly we can write this equation? This equation refers to first free body diagram here. Then you continue. Others still same. You apply the same. So what you see, okay, number 2, this number 2, which is a more direct one. So capital F2x equal to small f2x, and then there's number 2 on top of the force here. It means refer to element number 2. Okay, then the rest is just put in. So point number 3x here, point number 3 here, you will see 3x equal to force small f 3x1 plus force 3x number 2. Okay, if you look at point number 3, then you will get this equation. Okay, so it means that this equation referring to what is happening in this region. Okay. So you look at here. Okay, first step is just that why we start with this step, because this is a very simple direct case. And why you look at number 2 first, because it's also direct case. Right? Then the third one, I look at the external force. Right? So I always start with the external force first, with the capital F. In this case, I have three external force, point 1, point 2, and point 3. So with the capital F. All right. And then I continue with the analysis. Okay. All right. So again, recall the equation that you just learned just now. F equal to KD, or in expanded, you will see small f, small k, and u. So you just put what we established just now, right? The one on the left, this matrix is for element 1. The one on the right is for element number 2. Okay. Now, you expand the matrix into a formula, into a line formula. How you get this one? For F1x1, right? How you get this equation? Again, recall what you learned in matrix. You put this one, K, times this one. This is the first set. Plus this one times this one. Okay, that's why you get this first equation. What you do is that you take the first row of the matrix times the first column of the matrix, you get this equation. Okay. Lai, you okay with this formula? You understand how we get K1 U1 minus K1 U3?
Yes.
Okay, yeah, good. All right, then you continue to expand. Of course, this one you can do F3 first, lah. Right? So at the end, you'll get these three equations. Right? You do the F3. How do you get F3? You take this one times this matrix. So minus K1 plus this one. So that's why you get the the first one. Because you have the two matrix you have, will give you two term of your F3x component. So this is F3x1. This is F3x2. Because for the second matrix is from here, you take the first row times the first column here. You'll get this one. Okay, K2 times U3 times times negative K2 times U2, you get this one. Then followed by F2 times, right, take this one times this one, you get this one. All right. Before I move on, any question on these three equations? Any one of you not sure how you get these three equations from matrix? Anyone you're not sure or you lost? Try to get the concept rather than chasing after the numbers. Try to understand the step that the logic behind or how we get the answer. Okay, so we get these three equations. Then we put into matrix form again. Okay, these three equations we derive from the element matrix, right? Then we try to combine. We try to change these two. Actually, if you're good in matrix, we actually want to combine these two matrices into one matrix. 2x and 3x. And then we know that if you have three fours on the left, you will get 3 times 3 matrix. And then the displacement here, you will have U1, U2, U3. Okay. The next step is we try to build a complete matrix from these two matrices. This is 2 times 2, right? But if we combine these two, because we have three fours here, we have F1, F3, and F2. So we combine into a complete matrix here. So the next step, you're going to combine these two into one complete matrix. If you are good in matrix, then you can straight away put these two into 3 times 3 matrix. If you're not able to do, what you do is you expand the equation, like what we did just now, and then you put them back into this form. Okay, I'm going to explain how you put it back. I think we should go for a short break, but let me explain this one first, then we go for a short break. Okay, now we put the matrix form, these three equations into matrix form. Okay, how you do? The first step is always remember your matrix always in F equal to KD form. Again, force always with the curly bracket, K with the square bracket, and D with the curly bracket. So I'm very particular on a symbol when it comes to tests. So if you write your force in like that, you get the wrong answer. If you accidentally write the curly for your K, also get wrong answer. If you accidentally write the square for the D, also get the wrong answer. All right, I'll give you wrong answer. So again, the concept is still call back the F equal to KD formula. Okay, how do we put all this in one matrix? It's very easy. First, F equal to KD you look at the formula. Look at the formula. So for the force, you have 3, right? So you just put in the, you just follow. For the force, you have F1x, 2x, 3x. Then for the displacement column, also very direct. You know that you only have 3 displacement here, right? So you have what you see here, you only have U1, U3, and then repeat U3, U2, and U1, U3. So in general, you only see 3 movement, 3 displacement here. So you write U1, U2, U3 on the displacement column. Okay. Now I'm going to explain how you put the K component here. Okay. All right. Now, if you are okay, so you can actually break the matrix into coordinate. My method is I'll break into like that. I'll break into 3 column and 3 row because I know that I have 3 displacement here, or 3 free body that are free 3 degree of freedom. So I break my column into 3 and then row into 3 also. So I just write U1. This is my personal notes. You in your answer you don't write this one. So you just in your mind, in your mind map, you just do for the column, you write U1, U2, U3, and then this one also U1, U2, U3, and then you look at the equation. So you know that the first row of the matrix times this row will give you the first equation. This is the metric concept. So what you do, you look at the equation here. So you take K1 times U1. So what you need to fill in is just that you only know your U1. So how you get blank times what? U1 times what equal to K1 U1. So you just fill in K1 here. And then you look at the first equation. Is there any U2 in the first equation? No, right? There's no U2 here. So straight away use 0 for this space here. And then you continue with the third one. So you look at the third one here is U3. So in your equation, you have negative K1. So what you do is you just input negative K1 here. All right. So again, just repeat the concept of matrix. You take K1 times U1 plus 0 times U2 plus negative K1 times U3, you get the first equation. Repeat for the same for F2 and K and also F3x. Then you will know it will make sense to you that you will get this matrix. Okay. Anyone you're not sure how to write how to transform these 3 equations into matrix form? Anyone of you still blur? Good, huh?
Yes, okay.
Okay, yeah. Okay, good. Now, we already have a matrix form. So the next one is just to write everything in the. You just elaborate what you have there. So you know that your matrix is in the form of capital F equal to capital K and D. So your force will be curly bracket plus curly bracket F1 X2 X3 means you just copy what you see in your answer there. So and then the second one is the displacement D and then the K matrix here. So again, if you see capital F, it means global. Capital K means global. This one, you follow the others. So if the front F, capital F and K, this one become global also. If this one you see a small f means this one become local, 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 always local. Okay, this is how you develop the matrix formula from a system. Okay, of course in test you'll see value there, I'll give you value for false, K, and this one. This is just general concept. Okay, so what we learned in this example, we change element 2 times 2 matrix into 3 times 3 matrix. Okay, I think I stopped the recording.